Yeah.
Yeah. Okay. Thank you so much, for everyone for joining in, and I'm sorry for the delay. We had some technical difficulties, as well as we were waiting for a few more people to join in. Nevertheless, I hope now we can begin. And as told earlier, as told in the email which was sent to you guys, this session might go a little over an hour, because biostatistics is a vast field and has lots of concepts to cover. So it's difficult to do that in a matter of 2 to 3 sessions. So what we have tried to is optimize the times and however, I'll be trying my best to avoid boring you all out of this, and I hope that you all will enjoy. So, so today we are going with the first, we are continuing with the basics of biostatistics session, which was taken last time by Rajvi. Thank you so much, Rajvi, for setting the baseline and a foundation for what we are going to do today. And in the last session, I believe we discussed a lot of with Rajvi, discussed a lot of uh, points such as types of data and like what is categorical data, what is continuous data, and lot of the other aspects like when it comes to biostatistics. And these aspects are going to stay a foundation stone for this session as well as the next session. So without any further ado, let's begin. Uh, so to begin, I would like to, I believe Raji might have touched upon this topic a little, but I believe this is important for understanding what statistics is. So I will be taking this subtopic again, in brief. So firstly, before beginning, can one of you all tell me what do you all understand by statistics? Anybody, absolutely anybody. Would anybody like to volunteer? Maybe Ame, Aman, someone.
The study of data.
Yes. And what is biostatistics? And what I don't need a technical theoretical definition, but you can be more casual and tell me what do you understand by it. What are the applications of it and how we can use it.
Biostatistics basically includes collecting data pertaining to biological sphere and then analyzing it through the theorems and every concept that is available for the purpose of study and research.
Yeah, that makes sense. So, I would like to put it using an example here because I'm not very fond of again this theoretical definitions and being very wordy. So imagine here in this 10-15 odd people we are who have joined here. I want to understand what are the tea consumption rates in all of us. Okay, because I am a strong believer that I'm actually not, but like let's say for instance, I am a strong believer that tea prevents cancer, and that's why I really want to see how much you know how much effect tea has on cancer, and I want to prove it. Okay, so but we are not random people out there who will just say you have to present data because in biological sciences and biomedicine we have to prove something, and that's the essence of evidence based medicine, right? So I will collect the data of the tea consumption in between you all, and I'll follow up if anybody develops cancer in years to come, like maybe 10-20 years down the line. Okay, now some of us might not, God forbid. Okay, so like just for the purpose of this example, so the numbers we get are, are to be used. Okay, but imagine that tomorrow I go and tell, like, policymaker that, oh, these are the, the characteristics of people who blah 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 got cancers or tea consumption and whatsoever. It's difficult for them to understand, right? Because they are lay people, and also it does not like really affect or help us form policies or form like uh, interpretable uh, you know findings. So the process, I would say, from conversion of raw data, what we find in uh, find in researches, which to be converted into interpretations and conclusions, the midway, the chain between those is formed by biostatistics. Of course, as Deepika rightly said, that it also includes collection of data, yeah, like, but I would like, for myself, for for the purpose of this session, I would say that apart from that, it the main purpose of biostatistics is to link between two, like between your raw data from what you find in your study to actually interpreting and making meaningful conclusions out of it. So that being said, let's move on to the first topic, called as statistical distributions. In this subtopic, we're going to discuss various types of distributions we find in statistics and in mathematics. So like, there are various types of distribution. So imagine, I ask y'all, okay, the same question about tea. How many cups of tea do you have in a day? Okay, and like, somebody, Meha might say one, Shashank might say two, Hafsa might say four, I might say three, Raju might say four, again Vamsindran would say maybe one. So there are like many date there are many numbers we would get, right? From somebody might say 20, we never know, right? But if this were in a large population, okay, I'm giving just for the purpose of example. But if we do that in actual research, what we would find is the frequencies, that is the number of cups each person, the number one, that is one cup of tea per day, 2 cups of tea per day, 3 cups of tea per day. If we plot it in a graph, so we would find some type of shape, okay, of that graph. And that distribution, that visualization, and that spread of information across the spectrum is essentially called as types of distribution in statistics. And that is of prime importance, because the way our data is quote unquote distributed matters for how we carry out the further statistical analysis, as well as it guides us to uh, understand certain aspects like confidence interval, so that we can generalize to the main population. Okay, so just for the like, in your PSM or community medicine or family medicine classes, you might have heard something called as normal distribution. Okay, or in your ninth or 10th grades, maybe you all might have heard about something called as binomial distribution. Or there are, in a similar way, there are many such distributions which are available and known. However, in like basic biostatistics, what we frequently come across is normal distribution. But my point of saying here is that is not the uh, only distribution which exists in statistics. So coming to the normal distribution. So what is normal distribution? So it is also called as a Gaussian distribution or a standard distribution, in which you find a bell-shaped curve. So that is, if you collect responses of multiple people, let's have the same question: how many cups of tea do you have in a day? Okay, so from there, somebody might have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The number of cups would which most people would have will come in the center, right? But because it's a large population, what we would realize is that from that largest number, what we call as the mode, the numbers fall equally and symmetrically on both sides, as you know, so resulting in a graph what you can see as shown in the PPT. So this type of distribution is called as the normal distribution or Gaussian or a standard distribution, and it has certain characteristics. Like I told, it is symmetrical. That is around your mode. That is your highest value, and I believe mean median mode have been covered previously. So it falls symmetrically. It is not skewed like one of our previous. See, if you see the gamma or inverse gamma distribution or even F or any of this kind of distributions, there is a peak falling at one side. It is not symmetrical. Whereas some of the other distributions like normal T distribution or even your double exponential special types of double exponential distributions are symmetrical. Okay, so normal distribution is one of the, let's say, most used and ideal type of distributions, if I could call it like that, which is symmetrical, which is unimodal. That is, it has a single mode. Because in bimodal distribution, I don't know whether I have the image here, but in medicine, you might have heard about some pediatric renal cancers. Okay, like I've forgot which one it was, but certain diseases are bimodal. That is, the shape might be something like there will be two peaks essentially in the distribution, whereas in normal distribution, as you can see, it is unimodal. That is, there is a single peak. Also, it is asymptotic on both ends. That is, the two ends never touch the x-axis. That is, you can never say with confidence that some value will not be found. There is always a slight possibility that any of the values which exist, uh, any of the values which are possible, like theoretically, can exist in real world as well. Okay, for example, one person, there is a minuscule, like 0.00001% chance that a person might have 100 cups of tea, right? So that is what we called as it does not touch the x-axis, also called as asymptotic. And the last characteristics of normal distribution is that the mean, median, and mode in a normal distribution lie in the same, are the same, have the same value. Okay, but at the same time, we also need to be cognizant that there are certain non-normal distributions available as well. Okay, so I don't want to go into the details of each type of distribution. Okay, standard distributions which we have, but I want to discuss some characteristics of distributions which take a distribution far from normalcy. Okay, so as you know, when you have a symmetrical, first we'll talk about a symmetrical left and right symmetry, which is also known as skewness. Okay, so if it is symmetrical on both ends, we call it as a symmetrical distribution or a non-skewed distribution, we have for a normal as we have for a normal distribution. So normal distribution is a symmetrical distribution, but remember, not all symmetrical distributions are normal distribution. So coming back to this, a distribution can either be positively skewed. That is, the tail of the graphs will lie towards the positive. I'm not sure whether you're able to see the my cursor here, but the tail of the graph would lie towards the positive. And in such a graph, the mean would be more than the median, and which will be more than the uh, mode. Okay. Similarly, we could have a negatively skewed graph. That is, the values The tail lies towards the negative, that is the values more lie towards the higher end of it. That is, now imagine the example of tea itself. Okay, first of all, I'm not a tea connoisseur, but just I found that example very convenient for this purpose. So most of us maybe have 0, 1, 2, 3 2 cups of coffee per day, but some, there might be some which have 10 or 11. So if I were to imagine a graph, that graph would be a positively skewed graph where most of us might have 0 or 1 or 2 cups, and then lesser people falling towards the further numbers, of course, because negative number of cups cannot exist, right? Yeah. And now, why is this important? It's important to determine skewness of a distribution, because when I'll discuss this further in the next session about tests of significance. But essentially, certain tests of significance like the t-test or any of the parametric tests, I will explain what that means in the next session, could be applied only to data which has a normal distribution. That is, not all the data could be analyzed using parametric tests, or tests like t-test, etc. Similarly, even while you are expressing your mean median mode, like that is your central tendency as well as measures of dispersion, you cannot use the same thing for everything, for all types of distribution. You can use mean and standard deviation only and only if the data is normally distributed. But whereas if it's a non-normally distributed data, uh, we'll have to use concepts like the median, because as you can see even in these graphs, median shows a more realistic central tendency as compared to either mode or mean, and they're less affected by outliers, that is values which have the extreme, like as I told, a person may drink 100 cups of tea, I don't know, so those are outliers. So this is why it's important to determine whether a data is skewed or not. And for that, we use a test like the Shapiro-Wilk test or the Kolmogorov-Smirnov test. In due course of time, when you do your own research, you will come to know of how to apply this. But I am not going into the depths of it because of the paucity of time we have for this session. Similarly, we spoke about the left and right symmetry or the skewness. Similarly, we have something called as kurtosis, which is not very important, but I just wanted to let you all know. It tells about how narrowly the values are distributed. That is, a mesokurtic distribution is what a normal distribution might be understood. But whereas if the data values are very narrowly, scattered near the mean, okay, and near the mean or median or mode, okay, at that time we will find something called as a leptokurtic distribution, that is, which has a tall and narrow and a sharp rising peak. Whereas a platy, imagine a platypus, okay, or a plateau. So a platykurtic distribution would have something like values which are far from the mean. Okay, and this also matters when it comes to discussing what types of tests to use. But again, this is not very high yield for this session, so I will not go into the details of it. Okay, so now, like as I told previously, that the central tendency matters, when it comes to various distributions, and I believe Rajvi might have covered this in the previous, but I just kept this slide for the sake of the discussion. But when there is extreme outliers, or when data is not normally distributed, all my point is to recapitulate here is the most preferable measure of central tendency is median, and along with the median, what you use for measures of dispersion are interquartile ranges, that is the 25th percentile and the 75th percentile should be mentioned. Okay, So now what is a confidence interval? So now if you go back to the normal distribution graph, you will notice here that a normal distribution graph has a very accurate set of values which are distributed along its mean. Okay, so if you can see from -1 standard deviation to +1 standard deviation, we know that it covers a 68% of the of the sample parameters. Okay, whereas from -2 to +2 standard deviation, it covers more or less approximately 95% of the sample values. And similarly, if you consider from -3 to +3, it will consider almost 99.7 percentage of values which are found out from the data. That is, imagine now tomorrow you want to understand, let's say in a large population, you want to understand what is the size of their ovaries. uh, just I don't know what's the issue happening, but my laptop is, yeah, yeah, apologies for that. Just give me a moment, I'm sorry. Yeah, so here I wanted to say that imagine doing a research where you want to see the size of ovaries in prepubertal girls. Okay, and you collect data from a large sample, and you try to find put it in a distribution. Now essentially what we would expect is you would find a normal distribution. Now from that you would find a certain mean. Now, when you find out the confidence intervals from those values, these confidence intervals would say how much your values fall within the, like, your 95% of your sample values would range from this to this the for your given sample. So coming back to the topic, so confidence interval provides a range of values with a lower limit and an upper limit that are likely to contain the true difference or association in a population. Therefore, confidence interval of 95% indicates that if a study were to be carried out 100 times, the range would contain the true value in 95% of the times. So confidence interval provide more evidence regarding the precision of an estimate compared to the p values, which we'll discuss a while later. So confidence interval, uh, sorry, that's a repetition. Apologies for that. So it is an essentially interval containing 95% of the values. To construct this interval, what you have to do is you need your mean, a critical value, and a standard deviation. Okay. Now here is a small catch. You can either find a confidence interval of a sample, that is of your study sample, or you may find the uh, confidence interval of uh, of the population or for the population. So if you want to find it for a population, there's a concept called a standard error of means, which I'm not going to dive into in this session, but the whole purpose stays the same. So 95, so if you consider 95% confidence interval of a sample, that is in a research study, so it means that 95% of the values found out in that study are uh, like are so much to so much. Okay, and that's when we use standard deviation itself. But when we want to extrapolate that to a population, we'll use the thing called as standard error of means. Okay, so now we'll we'll go ahead with, I'll give some examples of how to calculate confidence intervals and interpret the confidence intervals. But here I I'll uh, just a minute. Yeah. So here the Z value will depend on the level of confidence which we have decided. Since z is from a standardized distribution, that is from a normal distribution essentially, this value does not change based on the sample size per se. So if you want a confidence level of 95% for a normal distribution, the value of z is 1.96. So that's why when you remember, our 1.96 is more or less close to 2, right? So that's why a 95% of the population lied between -2 and +2 standard deviation. Similarly, we do have values for other confidence levels, that is 90%, 99%, and so on. Okay, so let's take some practice questions for this session. So let us say that you are studying gestational age of newborns, which has a known mean and standard deviation of 40 weeks and 1.5 weeks respectively. Construct the 95% confidence interval for the population mean gestational age. Okay. So sadly, I was going to use my iPad, but due to unforeseen circumstances, I don't have access to my beforehand to write it. But basically here you have to find a 95% confidence interval, right? So here the mean is given as 40 weeks. So here we'll write below, we'll write as mean is equal to 40 weeks. They've also given the standard deviation, that is 1.5 weeks. So 1.5. Okay. So now if you want to calculate the confidence interval, we'll go back to the formula. So confidence interval is the mean plus minus the z into standard deviation. Okay. So here the mean was given as 40 weeks, right? So confident 95% confidence interval would be 40 weeks plus minus z. So remember the z is from your the confidence interval which we want, which is 95%. So 1.96, we can approximate it as 2. Okay. So uh, the 40 plus minus 2, and the standard deviation was given as 1.5 weeks. So 40 plus minus uh, 2 into 1.5. So 40 plus minus 2 into 1.5 is 3. So 40 plus minus 3. So what is the upper limit? 40 plus 3. 40 plus 3 is 43. Whereas the lower limit is 40 minus 3, which is 37. So essentially what we can say is from the given, in the given study. Okay, sorry, this should have been study. Sorry for the typo. Okay, confidence interval for the study mean gestational age. Okay, so this 95% confidence interval for this study sample would be 37 weeks to 43 weeks. Okay, now coming to the next question. Let me know if somebody wants to try. I think we can open the stage for this, and I'll help you all along. Does somebody here want to take this up specifically? We'll go slowly as per how we went for the previous one. Anybody from the audience? Avantika, Aman, Aryan, Astha, or maybe what we can do here is I will ask some simple questions and then you all can answer for that. Okay. First, tell me what confidence interval is asked. What percent of confidence interval is asked? Anybody?
95%.
Yeah, absolutely. So 95% confidence interval is asked. Now tell me what is the mean which has been stated?
3.2. 3.2 kg.
3.2 kg. Wonderful. Now what is the standard deviation which is given?
0.5 kg.
Yes, exactly. So now we'll go back to the formula. So does anybody remember the formula by any means, or we can go back and I'll show you the formula for confidence interval just in terms of mean and standard deviation, not the values.
Confidence interval is equal to mean plus minus Z into standard deviation.
Yeah, perfect. That's perfect. So now, since you have answered, could you help me with like uh, substituting the values in the formula? So 95% confidence interval will be mean. What is the
3.2.
mean?
3.2.
3.2. And what is the standard deviation? That is the sigma.
One. No, standard deviation is 0.5.
Zero point 0.5. Now we have they have asked for a 95% confidence interval, right? So
Yes.
now tell me, do you all remember what is the Z value for a 95% confidence interval?
1.960.
1.960. So for practical purposes, let's round it off to uh, 2. Okay. So now, can you take it forward, Deepika, as you have answered most of it?
Okay, so that makes it 2.2 the lower limit,
Yeah,
and
could you go one by one, like, telling, like, how I told in the previous question for our, other participants?
okay, so it will become 3.2 plus or minus 2 into zero point 0.5. So if we put plus for the upper value, the
Hmm,
answer is 4.2,
hmm.
and if we put minus for the lower limit, the answer is 2.2.
Yes, that's,
So the
yeah,
answer becomes 2.2 to 4.2.
yes, perfect. That's absolutely perfect. Does anybody want me to repeat of, how we did this? I'm really sorry for, not having access. I usually teach biostatistics using pen and paper method essentially on my ipad, but for this session, being it an official session, we thought we should go with the ppt, and that's why we are using this, but I hope it's still understandable. uh, Coming to the next, uh, so I think that clears, like, that is most of the, that is essentially what all would be understood by confidence interval. Okay. However, it is often confused with significance level and confidence level. Okay. So that I would solve in a brief while later on. But now, having said this, having, like, discussed all of this, we have to understand a concept called as hypothesis. Now, what is hypothesis? So in statistics, a hypothesis is defined as a formal statement which gives an explanation about relationship between two or more variables of the specified population. It helps the researcher to translate the given problem to a clear explanation for the outcome of the study. Basically, short mein bola, in very briefly, is basically hypothesis is your assumption. If tomorrow I want to uh, I'll like tomorrow, let's say I want to do a study. Okay. Or tomorrow I want to prove, as I told, a while back I was a strong tea supporter. Tomorrow, if I want to put forward a point, something on the lines of let's say uh, you know maybe running causes fibroids. Just a random thing. I am, let's say, misogynist, and I want to say, or I want to say that, like, uh, uh, yeah, let's say running causes fibroids. A random thing which I, strongly believe, like, how people sometimes believe Earth is flat. Similarly, I want to tomorrow prove that running causes fibroids, but I can't say that directly, right? I have to prove it. So here, my research question, which has been discussed by Zinab in the very first session, would be: does running causes fibroid in, let's say, women aged 30 to 40? Okay. Thir- okay, this is the research question. So my hypothesis, that is my assumption here, would be running is related to fibroids in women aged 30 to 40. So as it is as simple as it is. However, the one catch here is possibilities exist on two ends of the spectrum as well, right? I mean, if there is a positive, there has to be a negative. If there's a plus, there is has to be a minus. Similarly, when it comes to hypothesis, there are two types of hypothesis we consider, which work as a complementary pair, each stating that the other is wrong. Basically, imagine two arch enemies, or two strong opponents who are trying to make the other false. Okay, because both cannot exist at the same time, right? I mean, I cannot sleep and stay awake at the same time. I cannot let's say uh, I cannot write and erase at the same time. I cannot go left and right at the same time. Similarly, null hypothesis and alternative hypothesis are complementary to each other. Okay, where null hypothesis can be thought of as the implied hypothesis or a hypothesis of no effect. मतलब कुछ नहीं हो रहा. In like if I were to say in Hindi, so this hypothesis states that there is no difference between the groups, or there is no relationship between the variables, or there is no cause or effect, relation, or similarly. Basically, you have to be the most negative in your life. You have to say no, 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 and that's what null essentially means, right? So the null hypothesis is a presumption of status quo or no change. Okay, I think that is as simple as it can get. Whereas alternative hypothesis is also known as the claim or my belief or my assumption of what I want to prove. Okay, it might not be true, but I want to prove that. Okay, so what you expect the data to show based on your research on the topic. So let us take an example. So let's say a study was done to investigate whether family history of diabetes is associated with higher incidence of gestational diabetes mellitus in pregnant women, basically GDM. Okay, so firstly we should understand what is the research question. So the research question is gestational diabetes more common in women with a family history of diabetes? Okay, your null hypothesis and your alternate hypothesis, that is a hypothesis, essentially answer your research question, where there can be two possibilities. One possibility can be that it does not cause. Okay, so the null hypothesis, the H naught or the H0, would be gestational diabetes is not more common in women with family history of diabetes, right? So it is an assumption that you're opposite to your research question. It is the no answer to your research question. Whereas the alternate hypothesis would be gestational diabetes is more common in women with family history of diabetes. So it's an assumption or a yes answer to your research question. So in statistics, we cannot ever prove an alternate hypothesis directly. What we do in statistics is we see for the null hypothesis and we disprove the null hypothesis. So automatically, as I told, if one is wrong, the other has to be correct, right? But it's essentially like, imagine you like the theorems we did in mathematics, where we proved by contradiction, because we cannot prove directly that a triangle is a triangle, right? Or a square is a square, or some, I don't remember. So there we used to make a opposite or a contradictory statement to that, and we used to disprove or say that a contradictory statement is wrong. That's why our main assumption, our main statement is correct. Those theorem in mathematics we used to do in 6 or 7 grades. So similarly here, the main thing of statistics is that we cannot directly prove the alternate hypothesis. We have to assume that the null hypothesis is true, and then we have to work to disprove it. I mean, in case that is actually the case. Okay, I mean, sometimes the null hypothesis might actually be true, which will be coming to the point later on in this. Okay, so a researcher must disprove or reject what we called in statistical terms the null hypothesis first, and then it will automatically prove the alternate hypothesis. I'll take more examples just to be, this. So tomorrow I'm the crazy scientist, who does not deserve any nobles. Imagine that. Okay. And tomorrow I'm like, I again want to do some collage, and I want to say that um tubal tuberculosis, that is your fallopian tubes, tubal tuberculosis is caused by eating chocolates. Okay, yeah, I want to be I want to create controversies and get some Twitter likes and reposts, okay, and comments, and churn money out of it. But somebody then tells me, okay, prove this now first. So I will create a study, I will design a study where my research study would be, is eating chocolates associated with tuberculosis. Now, would anybody like to try the null hypothesis and alternate hypothesis in this? Anybody in the meeting? I mean, it's easy. Feel free to, and there's no right or wrong. Yeah. Uh, Deepika has raised her hands. Anybody else? Because Deepika really answered the previous question well. If nobody else is there, we could. Yeah. So Ovia is there. So please go ahead, Ovia.
So we can start. The null hypothesis will be that eating chocolate is not associated or does not cause tubal pregnancies.
Yes, perfect. And what would be the alternate hypothesis?
That eating chocolate does cause tubal pregnancies.
Yeah. I mean, we would prefer not to use the word cause because I'll come to that later. Okay, but like
Okay.
associated or related. But yeah, that's
Oh,
perfect. That's perfect. Thank you so much, Ovia. Uh, Kudos to you. And okay, one more example. So that was the answer. Okay, so okay, I had put tubal pregnancy in the in the slides, but still the same thing. What it's just for the sake of an example. Now the second example would be let's say, tomorrow again I am a misogynist. Let's say I'm taking by the way, a few misogynist example just because I like to make fun of or fun of misogynists, because that's what we are, we are here to support women's health and obstetrics and gynecology, right? So might as well. So in another example, in another time, in another dimension or another multiverse, I want to say that washing clothes causes pregnancy, and I want to prove it. Okay, as funny as it sounds, yeah, I mean, uh, might as well, I can think whatever I want. Okay, so my research question is washing clothes related to uh, getting pregnant? Okay, so what are the two hypotheses what you will find out? Now, I would like a new person again. Come on, it's easy. Anyone? Gumti, Avantika, Aman, Aryan, Shashank. Yeah, Shashank, go ahead, please.
Yes, washing clothes is related to cause pregnancy. That is the null hypothesis. And alternate hypothesis would be, sorry, the null hypothesis is washing clothes does not cause pregnancy, and alternate hypothesis is washing clothes causes pregnancy.
Amazing. That's perfect. That's perfect. So yeah, that is the answer. So I really don't have to explain, because the way you are paying attention and answering the questions, that's wonderful. So thank you so much for answering. And let's have a big round of applause for Deepika for answering the previous question, as well as Shashank and Ovia for this one. Thank you so much. At least
I
I
had
would
a
clap.
question.
Yes, sure.
So by nature, all null statements that we make, they are all just negatory statements, or do we make it the statement we definitely want to disprove? Like in the second
It's the
example,
actually
we
it's the
know for a
latter.
fact.
It's
Yeah.
it's basically It's actually it's the latter, like as in
Okay.
is the statement we want to disprove, or is the statement as we said status quo. It can be something positive. For example, if you want to do a research where basically now is the dengue season in Mumbai. I stay in Mumbai, and people say that what do you call it? Uh, your papaya leaves causes like improves platelet count. So I could like have like you can do it in two ways actually. One way could be your null hypothesis could be papaya leaf causes increase in platelet count, and you can disprove that. Or the easier way, because that's how statistical methods have formed, that you can in fact keep does not papaya leaves does not cause this increase in platelet count. And an alternate hypothesis could be papaya leaves causes increase in what do you call it, platelet count. And then just basically you can design the study. Imagine yourself that you want to prove that point, but ultimately when your results will come, it would accept your null hypothesis and make it like basically say that or conclude that papaya does not cause increase in platelet count. Okay, but you can go the other way around also. Like your null hypothesis can very well be a positive statement. So, but
Okay.
that tends
Um,
to make it more difficult. By experience is what I'll say.
okay. So my question was just that in the example two,
Yeah,
because we basically just want to disprove that washing clothes causes pregnancy, can that be the null statement?
yeah. I mean, it can, but again, like it would make just the further analysis difficult. Is what I would say.
Okay.
Yeah, so it's the better
Okay.
way or the simpler way is just keep what to go null and go for the null and alternate hypothesis by the uh, convenient way. I won't call it the correct essentially way, like it's nothing is correct or wrong here, but the more convenient way. And then your data will simply accept your null hypothesis, that will just say that your null hypothesis is true.
Okay.
So you get the point,
So
right?
it's just simpler to go for not statements for null
Yeah,
hypothesis.
exactly, that's what I would say.
Okay. Thank you.
Yeah. So thank you so much. That was a very insightful question, in fact, and I loved answering that. And if anybody has any other questions like these, I'm more than happy to answer. Okay. Now that's what we did. Now, okay. So now we came to the hypothesis, but now how do we further prove our hypothesis? That's the question, right? So that's what all the biostatistics is. So first we make assumptions about the population parameters. Population parameters here means anything. It could be your hemoglobin level, it could be anything, absolutely anything. Okay, which is essentially your hypothesis. Okay, now to do this, to prove or disprove anything of this, we'll have to do the study. So there we'll collect the data. Once we collect the data, we'll calculate some statistics, or we can dive into the statistical parameters of the data. And then based on those data, we'll evaluate a hypothesis, our hypothesis. Okay, let's give an example. We want to I'll give an example related to let's say the because Ovia pointed out with um very nicely to that example and brought to the forefront. So I'll go with that example itself about washing clothes and pregnancy. So our assumption, null hypothesis, is washing clothes does not cause a pregnancy, and alternate is washing clothes causes pregnancy. Then we'll find out we'll collect data where we will find out the number of times a certain person washes clothes, and to the, let's say, number of clinical fertility rates. Okay, and then we'll do statistical tests. In this case we might do something like a t-test, or maybe something like a, let's say, correlation analysis. Okay, once we do a t-test or correlation analysis, we'll find out uh, the t value or a r value respectively. Again, that is to be covered in the next session, so don't sweat about it. But we'll find out a statistical parameter, that is, each statistical test would give you a certain value, okay, which you can't directly put forward to your, people you want to prove this to, because they don't know. For them, t is for t, p is for porous, p is for panda, p is for whatever, or pony, or T is for let's, I don't know, tandoori, because I'm hungry right now. But sorry for this bad jokes. But yeah, essentially, you'll find a number using the statistical test, and that number will also give a p-value, and this together will have to be used to evaluate the hypothesis, in which there are two options. It can either accept the null hypothesis, or it can reject the null hypothesis, which in turn also means proving the alternate hypothesis. So that's what it is. So in hypothesis testing, we find out how likely a parameter is correct. That is validity of our assumption. So imagine tomorrow I do a study uh, comparing the rate of fibroids in Mumbai and Vasai. So Mumbai, you all know, is a city in the north, in the western coast of India, just for definition. And Vasai is a town where I am from, which is in the suburbs of Mumbai. Let's call it a rural place. So our we'll find out an assumption or a hypothesis based on this. So my hypothesis, let's say a random one, would be fibroids in Vasai are more than the fibroids in Mumbai. This essentially would be our alternate hypothesis. Our null hypothesis would be no difference, right? So there is no difference in fibroids prevalence in between people of Vasai and Mumbai. Then I will conduct the study, and what I'll find out, the data from my study sample is this is 50% and this is 40% at the age of 30, let's say. But tomorrow, like, I cannot just randomly say ki, like, this is 50%, this is a 40%. This has no meaning, like, whether it's significantly different or not. I mean, like, 51 and 49 are also Vasai more than Mumbai, and 50 more than 40 is also Vasai more than Mumbai, and 90 more versus 10%, or 90 versus 20% is also more than. So, we have to carry out the statistical tests to essentially tell how strong is the data, or how significant essentially is a data, to generalize and to apply it for a conclusion. Okay, so here we'll carry out a test. Let's say here maybe it would be a chi-square test. Okay, and then that test will find out a chi-square value and a p-value, and then we'll find out whether there's a significant difference or not. Okay, so that's what it is, what we spoke about a while back. Okay, similarly, another example when it comes to this, when it comes to blood sugar levels, or something I want to talk about, quantitative parameters. So I want to do a study where just of on gestational diabetes, oops, sorry, like, I mixed up the two examples. But let's say I want to conduct a study related to effect of daily cola consumption on gestational diabetes mellitus rates. Sorry for the typos, extremely sorry. In Forget the age. Okay, so effect of daily cola drink consumption on gestational diabetes mellitus rates. Okay, we want to find out whether cola drink affects GDM. Okay, so one possibility, it does not affect. Okay, so in that sense, in that case, the mu, that is the mean value of blood sugar levels of cola drinkers, will be equal to the mean value of non-cola drinkers. Okay, which essentially proves a null hypothesis that there is, which is essentially similar to a null hypothesis that there is no difference in GDM incidence in women who drink cola daily versus those who do not. The other possibility is it can affect. So the mean values won't be similar, right? So that is essentially on the lines of an alternate hypothesis. Now we know, let's say that it is not the case. Cola drinking, let's say, does not cause GDM. Okay, the reality is that, and a study also finds out that. So in our study, we would find out that the mean values of blood sugar levels of cola drinkers versus those who do not drink cola would be similar. Okay, and hence we would accept the null hypothesis. So our research statement would be false and we would accept the null hypothesis. Whereas the other option, if it really affected, and if our study also found out similar, and essentially our study would find out that the mean values are not similar. Okay, in such a case we would reject the null hypothesis, and automatically our alternate hypothesis would get proved. Okay, similarly for IVF, now, like, I had added a thousands of examples. Again, like, let's imagine I create a new drug tomorrow for IVF for uh, there's an antagonist cycle in the IVF for getting more number of oocytes, okay, or more number of mature follicles. I call it Pauras relics, and I want to we have to compare it to something, right? So let's say we compare it to Gani relics. So the two options would be does not work or it works. So in if it does not work, the oocyte yield rate would be similar, and hence our statistical tests would give a value which would prove or accept the null hypothesis, and the other way around for if the oocyte yield rate is different. So that's about those examples. But here you have to, one catch here I would like to mention is there is something called as a one-tailed or a two-tailed test, which depends on the alternate hypothesis, wherein one option, okay, let's consider this option itself. Okay, I want to prove that my drug, Porous Relics, is like I want to compare it to Gani Relics. Okay, so or let's say, let's take the example which is given below. Okay, I do a study which wants to see whether there's a difference between the sex toys used between boys and girls. Okay, so I don't care about which type of whether boys is more than girls or girls is more than boys. I just want to see whether it's equal or not, if there's a difference or not. And in such a case, I would go for a two-tail test, wherein your null hypothesis would just say that A is not equal to B. Okay, we don't care about whether A is more than B or B is more than A. Okay, we just want it not equal. Okay, so that is called as a two-tailed test. That is essentially we are fine with going either above towards the positive side of the normal distribution or the negative side of the normal distribution. We are totally fine with it. Okay, but there might be uh, cases where we want to specifically see if there is an increase, or in other example we want to specifically see if there is a decrease. Now let us take example, for example, uh, so let's say a study where we want to find a difference between cardiac deaths in patients taking new drugs. Okay, we have, like, found out a new drug which decreases sudden cardiac deaths. Okay, so uh, are so the rate of sudden cardiac death in the patients or the group taking the drugs will essentially has to be lower. We cannot, we're not fine if a drug is causing higher death rate due to sudden cardiac arrest, right? So in this would be a one tail test of a lower tail, wherein we want our alternate hypothesis to be lesser than our null hypothesis. That is our interventional group. Let's say, just for the sake of example, our interventional group We want it to be lesser than the uh, no difference group. That's what essentially a one-tailed test means. Similarly, we can have a upper-ended one-tailed test as well, wherein our alternate hypothesis would say that a new treatment or a certain group is higher or more than the other placebo or the you know baseline of reference group. For example, if you want to see the quality of life between people taking GnRH agonists because of its, let's say, effect on endometriosis or fibroids, okay, agonist or antagonist, either ways, okay. So we would expect that the quality of life would be better because the bleeding is less, the pain is less, and a lot of other issues when it comes to fibroids and endometriosis are lesser, right? And hence, we wouldn't want their quality of life to get, uh, you know, uh, worse, right? We want it to get better. So in this case, we would use the upper-ended test, wherein uh, in our interventional group who is taking GnRH agonist, would want their quality of life to be only and only better. So that is what a one-tailed or a two-tailed test is. Okay. Now you have done, imagine you're going through this journey through all of this, okay? But ultimately, like you have come to an end where you find out the t value or a chi-square value or a r value and lots of other statistical tests which have tons of different values. But you want to convert it to a more, free, understandable and a more standardized value. That is what a p value would do. And essentially p, like, you can consider the p for probability, wherein what is, sorry for the typo, this was the last minute thing. So a p value is used in research to determine whether the sample estimate is significantly different from a hypothesis value. Essentially, whatever you have been speaking from so long, whatever have been yapping from so long, so the p value is a measure that helps determine the significance of the results obtained from a statistical hypothesis testing. So what does this mean? So p value is the probability of obtaining test results at least as extreme as the observed results. Basically assuming that the null hypothesis is true. Or a p value is the probability that the observed effect within the study would have occurred by chance if in reality that was no true effect. Imagine, essentially imagine the example of washing clothes and pregnancy. We know that that's not true, okay. But if our so p value, if when we do a study and find out the value, so p value from our data would tell how significant our results are by telling the probability that the effect, the results what we found out in our study were by chance or not. So if it is of by, like, most of the results were by chance, let's say 60% of them were by chance, we wouldn't be happy with those results, right? Because if 60% is happening by chance of washing clothes causing pregnancy, I mean, then that's not something I would believe. Whereas if only 5% or let's say 1% of the results are happening by chance, then we're fine with it, because the other 99% is the true thing which is reflecting what is happening in the real world, right? I hope this is making sense. I'll take some examples in the coming time, but let's say a low, so how to interpret this? A low value, p value, which is decided by the significance level, okay, typically less than 5%, that is 0.005, indicates that the observed data is unlikely under the null hypothesis, that is unlikely by chance, and that suggests that the null hypothesis should be rejected or may be rejected, and which consequently proves the alternate hypothesis. Whereas a high p value, that is more than 0.05, suggests that the observed data is consistent with null hypothesis, meaning that there is not enough evidence to reject it. Okay, so let's take an example. So a statement would be drug 23 reduced patient symptoms compared to drug 22. Okay, patients who received drug 23 in a sample of 100 were 2.1 times less likely than patients who received drug 22 in a sample of again 100 to experience symptoms of disease A, where a p value was let's say 0.03. So this means that the probability that this reduction of symptoms happened by chance alone is just 3%. 97% of the times it's not by chance, it's the actual thing, is the actual what you will find out in the real world. Okay, so uh, that's what the p value would tell you, that how strong or how statistically significant your results are. Okay. Or in a, like, let's say take an other example where individuals who prescribed drug 23 experienced fewer symptoms compared to individuals who were prescribed drug 22. This finding was statistically significant with p of 0.02. Here, here they have given mean and standard deviation, but essentially you can see comparing the both examples. Although one is talking about risk ratio, another is talking about just means and standard deviation, which will ultimately have to be tested using t-test or something like that. uh, but both ultimately are giving p-value, and that helps us to more so interpret results in a easier way. But now the point here is, while doing this, we may come across some errors. For example, let's take an example of birth fractures in GDM babies versus non-GDM babies. What we know in reality is GDM, that is gestational diabetes mellitus babies, are more prone to birth fractures, birth trauma compared to no GDM, like in cases where there is no gestational diabetes mellitus, because gestational diabetes mellitus causes macrosomia, right? So then, but we still want to do a research. Like imagine this was not known like, years back. If a result says that the birth fractures incidence is not similar, that is what is there in reality. So that we are fine with that. But if our research states that again, sorry for this, GDM is equal to no GDM, then that is essentially an error. Okay, where in spite of there being a difference, okay, we are saying there is no difference. In reality there is a difference, but we are accepting the null hypothesis, uh, and this is what is called as a type 2 error. Okay, so what are errors in biostatistics? Those are critical concepts that pertain to inaccuracies or uncertainties in any of the techniques in biostatistics. Understanding these errors are essential for proper data analysis and drawing valid conclusions. There are two main types. Okay, so now imagine if reality is saying both groups are similar, and if we find both groups are similar, okay, then that is fine. If reality is saying that both groups are, the last thing I have written, if both groups are not similar and we find out that both groups are not similar, and that is also fine. But if consider a situation where both groups are similar, but we find out that both groups are not similar, that is we are reject rejecting null hypothesis, in fact when it's true, that is called as a type 1 or alpha error. Whereas if in reality the both groups are not similar, then but we call it similar, that is we accept null hypothesis when in fact it is not true, that is called as a type 2 or a beta error. So, null hypothesis in type 1 error, null hypothesis is true but rejected. So, in the probability of type 1 error is given by the p value, as I told earlier. Okay, the significance or the alpha level is the maximum tolerable probability of type 1 error. Alpha is fixed in advance, that is, we decide before we start a study, and p value can be calculated can be less than equal to or greater than alpha, whatever a studies say. But only and only if our calculated p-value is less than the decided alpha or the p-value cutoff, then we call it as the findings are significant. We have to keep the type 1 error to be minimum, then the results are declared statistically significant, as I told. However, there can be type 2 error where null hypothesis is false but not rejected. Or in other words, null hypothesis is false but is accepted. The probability of type 2 error is given by beta, but type 1 error is more serious than a type 2 error, as you might already understand. Now, what is power? It is the probability of rejecting a null hypothesis when a predetermined clinically significant difference is indeed present. Okay, so what does this do? This measures the ability to demonstrate an association when one really exists. So the word itself is self-explanatory, that it tells you the power or how strong the study is. So because that if the type 2 value is type 2 error is decreased, of course if your error is decreased, the strength of the study is going to increase. But remember, the term power stands for, is corresponding to your type 2 error, whereas your significance level corresponds to your type 1 error. Okay, so power of a statistical test is the numeric representation of its sensitivity. Okay, now how to increase power of a test? We can increase, or a study for the matter of fact, we can increase the number of subjects in a trial. That is, we can increase the sample size. We can reduce the probability of type 2 error. Okay, that is decreasing beta. And how to do that? When you decrease beta, then during a sample size calculation, automatically your sample size will increase. So essentially, point 1 and point 2 are increased, so are related. Point 3 is about increasing sensitivity. This is about diagnostic tests, which I'll cover in the next session. And as I told, the point 4. So essentially, sample size, the more your sample size, the more your power of the test. That is less type 2 error or less beta. But remember, the more you have your sample size, the effect on alpha also changes, because these parameters are sensitive to sample sizes. And essentially, it happens after a point that if you the more you decrease beta, the more alpha will increase. And if alpha decreases, so you cannot make a study perfect. In ideal, ideal scenarios don't exist, so you can't decrease both alpha and beta, but alpha is more important than beta, so we have to try to decrease alpha as far as possible. Okay, but there is this one concept which people do get confused a lot about: the confidence level, significance level, and confidence interval. Okay, now I'll differentiate the two by just saying your significance level. Remember, your significance level is what we researchers decide or assume before the study. Okay, remember this very carefully. Whereas your confidence level and your confidence interval are found out after the study by calculation, that is the data of our study. Again, your significance level is what you assume and decide before you start the study at the protocol designing stage, whereas your confidence level and confidence interval would be something which you will derive from your or which you will use while speaking of your results. Okay, your confidence interval and confidence level are the words which you'll use after you complete your study. Okay, so a significance level is what we researchers decide or assume. That is how accurate we want a finding to be. So essentially, your alpha and your beta related to your significance level, more so beta. So how does beta affect? So beta will affect the sample size calculation, and the alpha will as well as the alpha and the alpha. Okay, remember, alpha is 1 minus the significance level. So if we say we want a significance level to be 95%, then our alpha, that is type 1 error probability, would be 5% or 0.05. And in this case, when you use this, like, for your statistical test, for your significance level, your critical p-value, that is your cutoff of p-value, what we said, is usually 0.05, but that is not always true. We are allowed to use our own p-values, but 0.05 is more or less a convention which has been set up in the world of biostatistics. Okay, so when we decide if our study has to be 95% significance level and calculate sample size of that, then after do your research study, you cannot say that I want to change my p-value cutoff to 0.1. That is not how it works. Okay, if you decide something beforehand, that has to stay afterwards. Only then your sample size calculation and your statistical test inference would go hand in hand. Otherwise, there will be an error. Whereas your confidence interval and confidence level are found out or spoken about after the study by calculation using the data of the study. So they tell how strong the study data actually is. Okay, wherein your confidence level will tell about the repeatability, whereas your confidence interval will tell about the generalizability. Let me give an example. So imagine the wonderful Rajvi did a study on the levels of TSH in pregnant women. She had decided her significance level to be 95%. That is alpha is 5% or 0.05, the cutoff value. Okay. So this was important in calculating a sample size and determining the p-value cutoff for later, but it has to be decided early on itself. Okay. So significance level is decided beforehand, and it is important in calculating sample size and determining p-value cutoff. Okay, then she did her research and she found out in her population that the mean was 4.15 milli-IU per liters, and the standard deviation was 0.35 milli-IU per liters. Now this we can also write it as TSH is 4.15 plus minus 0.05. That's how you write mean plus minus standard deviation with a 95% confidence level. Okay, uh, because that's how you will, like, tell your study findings. But this mean and standard deviation can be used to find out your 95% confidence interval, which is mean plus minus 1.96 into standard deviation, the same thing which we did a while back. So the values of the same would then come out to be 3.45 to 4.85 if my calculations haven't been wrong. But basically, essentially, 95% confidence interval will derive from these two numbers. Now, what does this 95% confidence interval will tell you? That your population values, 95% of those population values will lie in the confidence interval which is given by Rajvi. Okay. Whereas this 95% confidence level, what will this tell you? That if Rajvi repeats her experiment or study 100 times, we are 95% confident, or we can say that 95% of those times that the repeat results will have similar values like what the initial findings are. Okay, so again, to recapitulate, significance level decided before the study. Okay, and used for calculating sample size and p-value cutoff, whereas confidence interval talks about the generalizability, that is the population values, whereas confidence level speaks of the repeatability. Okay, so I think I'll skip this topic and keep this topic for later. Okay, for now, let's do some sample practice questions quickly. I won't take this long because I think thank you so much for I think most of you all have, like, stayed, and but I would like to take this a few questions. So first question I will answer, then next question you all can answer. Okay, so the question here is, a study evaluates the effect of new prenatal care intervention on maternal mortality. The relative risk of maternal death with intervention is so and so and so, with confidence interval of so and so. The p value is 0.12. Okay, so what which of the following conclusions can be made on this data? So here we have to assume that the p value cutoff is 0.05. So can somebody tell me whether 0.012 is lesser than 0.05 or greater than 0.015? Anybody? Just unmute and say.
More.
Hello? Yeah. Yeah, go on, Ovia.
Yeah, the p-value is more than
Yeah.
0.05.
So remember what we spoke about a while back, that if a p-value is greater than the cutoff of 0.05, it says that most of it is because of chance. Essentially, we want the p-value to be as less as possible to be significant, in which isn't true in this case. So let's go over the statements one by one. So the intervention significantly reduces mortality. I don't think so, because the values are not significant. It is showing a relative risk lesser, as in, so the intervention is somewhat showing a reduction in maternal death. However, the p-value is not significant. So the results are not significant. So we cannot say it significantly reduces. Second statement, the intervention may reduce maternal mortality, but the results are not significant. I guess this is exactly what we discussed, right? Like with what I told right now. So B is the correct answer. The intervention increases maternal mortality. That's not the case, because the risk ratio, relative risk is less than one. And Zainab and Rajvi have spoken about this in their previous sessions about, if relative risk is less than one, then it is decreasing. Whereas if it is more than one, that is increasing. So definitely not C. And option D is, there is no difference between the intervention and control groups. This can also be the right answer, but amongst B and D, the best option would be option D, because it is saying it may reduce, but the results are not statistically significant. Okay, because like uh, this is a more specific and to the point and answer. Okay, so I will go with option B more, and the second option, if I were to go with anything, would be option D. Option A and option C are totally wrong. Okay. Next question. A meta-analysis examines the effect of folic acid supplementation on incidence of neural tube defects. The pooled relative risk is 0.35 with a 95% confidence interval of 0.25 to 0.45. P-value is less than 0.001. Which of the following statements is correct? Now, does anybody want to try? Absolutely anybody. It's fine, even if Dr. Deepika, Hafsa, Meha, Ovia, Aman, Aryan, if anybody of you all are there, Sashank, Vamsi Dharan.
Is it D?
Yeah, it absolutely is. Okay, now let's go one by one. Firstly, we'll see whether the p-value is less than 0.005. It is less than 0.001, which means it is significant. So one thing we found out, it is significant. Secondly, what is the pooled relative risk? Okay, so the relative risk is 0.35. So we know that relative risk, the reference number is 1. Okay, so it has changed from 0.35 from 1. So imagine 1 as your 100% and it has gone to 35%. Okay, so essentially you can say that the uh, incidence of neural tube defects in those taking folic acid supplementation is 0.35 times, or you can say that it reduces by 65%, because 100 minus 35% is 65%, right? We can say as that. So and the confidence interval which they are showing is 0.25 to 0.45. Okay, so the reduction could be 25% to 45%. Okay, uh, so we'll go through our statements one by one. So, does folic acid have no sub effect? That's not true because our findings are significant. And option B, folic acid supplementation reduces the risk of neural tube defects by 65% and the result is statistically significant. Yeah, that's what we discussed just now. Option C, the results are inconclusive because p value is too small. Not the case. P value is too small. That's why those are conclusive and significant, right? And option D, true risk reduction could be as low as 25% or high as 45%. Now, this statement is not true because although these values do tell the 95% confidence intervals, but remember that tells about a 95% population parameters. For the 5%, it could be even below that, or even means it can be even higher or lower than that. Okay, that is, it can cause more reduction or cause lesser reduction. Because remember what I told in normal distribution graph, it is asymptotic. That is, at no value will the probability be zero. You can find any value at any you can find you there is a non-zero probability of finding out absolutely any value. So this definitive statement that it could be as low as 25% is not essentially correct. Okay, now this one, a study of maternal dancing and placental abruption reports a relative risk of 2.2 with a 95% confidence interval of 1.5 to 3.2 and a p-value of 0.6. Just consider this 0.5 to 3.2 and a p-value of 0.6. Which of the following is true based on these results? Does anybody want to try? Meha or Hafsa, Shashank, if you're still here. Aman, Aryan, Ovia, Deepika, y'all may try. I think y'all are only more responsive right now. Yeah, Ovia, you can go ahead.
Is it D?
Yes, I will say that there are two correct answers here.
Okay. Um,
A and D.
Sorry, Deepika, Dr. Deepika, you said something?
Yes, A and D.
Yeah, that's a perfect answer. So as we know, p-value, we assume the cutoff to be 0.05. Okay, like when nothing else is given. So if 0.6, so it's higher than that. So it's not significant. Okay. So here I have not even added things like relative risk interpretation. Here I would simply say that it is not significant. So dancing is not a risk factor for. So that's correct statement. B statement is associated with statistically significant increased risk. No, absolutely not. Option C is confidence interval indicates a significant risk of placental abruption. My bad about this, it should be 0.5 to 3.2. Okay, because if it is 1.5 to 3.2, the p-value won't be 0.6. I mean, that's how it is. Like if both the values of the standard deviation fall on one side of the reference mark, that is, for relative risk the reference mark is 1, for correlation analysis is 0, for uh, and so on, right? Relative risk and odds ratio, the reference range is 1, right? So if both values of this 95% confidence interval fall on one side, either more than 1 or less than 1, if both the side, then the p-value definitely comes out less than 0.05. So that was a error in typing. So here consider it 0.5 to 3.2. That would make the confidence interval non-significant. And option D is p-value suggests the result is likely due to a chance. That is true. So option A and option D are correct. And if there was if there was not a typo, because there is a typo, even option C would be correct, but apologies for that. Now I'll take this as the last question for the day. Okay. Uh, the following table represents a meta-analysis. Okay, C-section and postpartum hemorrhage. Which of the following conclusions is supported by the table? We'll go one by one. Okay, tell me right or wrong. Firstly, elective cesarean section is significantly associated with increased risk of postpartum hemorrhage based on overall odds ratio. Okay, so okay, I forgot to put the overall odds ratio again, my bad. But I'll say the overall odds ratio was 1.4 with a confidence interval of 1.2 to 1.6 with a p-value of 0.008. Okay, so what will be your interpretation? Overall odds ratio from the meta-analysis will be is 1.4 and the p-value is 0.008. So what will you call overall odds? Like, is it significantly associated?
No.
Sorry, 0.008 it is with a cutoff of 0.05.
Okay, then it is.
Yes, then it is.
Yes, it's a
Yes, because I said 008, not 0.08. So yeah, yeah. So statement A would be correct if I give the extra information. Option B is elective C-section does not increase the risk of postpartum hemorrhage uh, as per study D. Okay, so just I want you to interpret. Forget the statements. I want you all to interpret all the studies one by one. First, tell me is study what does study A say? Okay, I did hear. I think Sashank speaking. So, do you want to try? Just tell me your
In
interpretation of study
in study A, it is significant because p-value is 0.002.
A. Yeah.
So it is
Yeah,
below the
and as you
cutoff.
can observe, because the p-value is 0.002, your confidence interval are also both the numbers, both the limits of confidence interval are more than one. So even if, okay, in such a case where they don't give you p-values, but give you confidence intervals, that also is enough actually. Okay, at times. And odds ratio is, so it's saying that a C-section is increasing. Okay, I also want that statement that because the odds ratio is 1.8, so it is a increased risk in elective C-section. What about study B? Anybody else? Aman, you there?
Yeah, it is significant in study B2.
Yes, and is it increasing the risk or decreasing the risk?
Increasing, I suppose.
Yes, because the reference mark is up 1, right? So
Yes.
anything above 1 is increasing.
Right.
Absolutely correct. Aryan, if you're there, can you interpret study C?
I think it's increasing.
Yes, and is it significant? Is it significantly increasing? Is what I mean. Yeah. Assume the cutoff of 0.05.
Yeah, it is.
Yes, absolutely. That's perfect. And in study D, anybody? Vamsi Dharan maybe or K Gomti, like she was there a while back. No, she's not here. Meha, maybe if you're here, if you're listening. Okay. Anybody? Absolutely anybody who wants to take up study D.
study D will not be statistically significant. The p-value is
Exactly.
higher.
Yeah. The odds ratio is saying that the odd there is an increased risk because it's still more than one, right? But study D does not have a significant finding because it's more than 0.05. And if you observe, as I told before, because the lower limit is going below 1, that's why it's the p value is also not significant. So that's how confidence interval and p value is kind of related, like I won't go into the depths of it, but that's how it is. Okay, so forget this options. I just want y'all to know how to interpret the studies. Okay, okay. Sorry, one last question. Okay, so and this one is like kind like this, like two last questions I'll take. Okay, I'll just tell you how to do this. So in a study of pregnancy outcomes, the mean weight gain during pregnancy was 14 kg with a standard deviation of 2 kg following a normal distribution. What is the percentage of pregnant women are expected to gain between 12 and 16? So tell me first. So 14 is the mean and 12 to 16 is asked. So how many standard deviations it is apart? So 14 plus 2 is 16 and 14 minus 2 is 12. So it is 14 plus minus 1 standard deviation, right? Mean plus minus 1 standard deviation. And if you go back to our reference material, then the values presented by minus 1 to plus standard deviation is 68%. So that's how you do. You'll first check the mean, okay, then you'll check the standard deviation, then you will compare, okay, you will compare the mean with the upper value and see how many standard deviations they are asking in terms of, okay, and then you will check and then you will see the percentages. Okay, if they had asked 14 to 16, between 14 to 16, then that's only one side of the graph, right? So the answer would have been 34. I hope this is understandable. Similarly, this question, they have given a mean of 39 weeks and a standard deviation of 1 week. The woman delivers at 37 weeks. Now tell me how many standard deviations it is apart. Anybody?
2 minus 2.
2 minus 2, right? So yeah, that's the answer. I mean, it's as simple as that. Okay. Like for those who do not understand, the actual weeks she delivered was at 37, when the weeks is 39. So she delivered at a minus 2 week. Okay. But if the minus 2 weeks, but the standard deviation is 1 week, right? So the Z score would be, because if you divide it by 1 week, then it would be like just minus 2, right? So the answer is B, minus 2. Okay, and this is the last question I want somebody to try. Does anybody want to try? The mean hemoglobin level in pregnant women is 12 gram per dl with a standard deviation of 1 gram per dl. Approximately what percentage of pregnant women would be expected to have a hemoglobin less than 12 gram per dl? Remember, 12 gram is the mean, and they're asking how approximately what percentage of people, pregnant women would have hemoglobin less than 12. So just imagine the graph and raise your hand for now for this one, because yes, Aman, Aryan, do you all also want to try? Don't say the answer, but do you all want to try? Remember, the normal distribution graph is similar across the mean. So that's a hint. So okay, Ovia, Deepika, Aman, Sashank, at the count of 3, 2, and 1, y'all can unmute and say 3, 2, 1.
50.
50%.
Yeah, perfect. That's wonderful. That's lovely answers, and it's great to hear those. So yeah, that was the last question from my end, and thank you so much. Do you have any questions about this session? Y'all want me to answer? One thing I would ask is, for like some of the concepts I would be recapitulating and like recapping, and so, recapping just sounds weird. Okay, recapitulating in the next session in conjunction with a few more topics related to statistical tests and association versus correlation versus and other topics. Okay, so for questions related to those could be kept for later. But if there is something specific you want me to answer related to this session, I'm more than happy to answer now. Yes, Dr. Deepika.
Sorry, I mistakenly left my hand raised.
Okay. Sorry. At this moment, I would like to really thank every one of you for, although the number of people attended was limited, but all of you all, like most of you all, apart from one or two, stayed till the end, and I'm really grateful to you all for waiting and like hearing. I hope it was helpful for you, and any feedback would be appreciated. As far as the time is concerned, I'm so sorry for overshooting the time so much, but honestly, biostatistics cannot be taught in a matter of like 2 sessions. So that's where and especially when I have to take a lot of I like to take a lot of examples. Next time I would make sure that I have my iPad access, and so that I could like draw and show. And next time I'm also going to show a demonstration on laptop on how to use the jazz software. So I'll ask you all to I would ask you all to please download that and attend. It would be really interesting. That being said, a form would be sent uh, uh, is sent on the post event form. I'd request all of you all to fill it for the purpose of certificates. A couple of people, I think Meha and Deepika, did leave before, like, before sending the form. But I think Rajvi, do we send it on the group, right, as well, or we doing or something like
We don't normally send
email?
it on the group,
Yeah,
but I can send it to the participants who
we
left.
can send it on email for the participants who are like attending today, if that makes if that is a thing. How does that sound?
Yeah, that sounds good.
Yeah, we can email them. Yeah. So we do have the attendance records, so not a problem. So certificates will be issued only to those who are attending. But again, thank you so much for attending. So until next time, and please share any feedback you all have for the next session, and I'll be happy, more than happy to take that up and improve my ways of teaching as much as possible for the next session. Thank you so much. We can end the meeting here, right, Rajvi?
Yeah.